Okay, this is lesson 6.3, linear models. Tables, graphs, and equations are all examples of mathematical models. And in this lesson, we're going to look at linear models. A linear model represents quantities that increase or decrease by a constant amount over equal intervals. So if we look at a table of values, we should identify the first differences as being constant. If we look at a graph, we should see a straight line. And if we look at the equation of a line, it should look like y equals mx plus b, where m is the slope and b is the vertical intercept or y-intercept. The key here is that the rate of change is constant. So we're going to compare some tables, graphs, equations and see if we can identify which one's the line. So first we have two tables. We're going to look for a table that has a constant first difference. So if we look for the first differences, what's happening between consecutive y values, we'll look for ones that are changing by the same amount. This table, the first difference is negative 5 because we're going down 5 and then down 15 and then down 25. So this one is not linear because it's not constant. The second table, if we look for first differences, all the values are going up, and the first one's going up by 40, the second also up by 40, and the last also up by 40. Since the first differences here are constant, we have a linear relationship. The graphs are the easiest ones to tell. You're looking for the one that's a straight line. The first one that is a straight line. So this is the linear model. And we have to give a reason. So because the graph is a straight line. And the second one is not linear, or we could say nonlinear. And this is because the graph is a curve, or not a line. Last one's the equation. You're looking for the y equals mx plus b, but it might not always be written in y equals mx plus b form. So what we're really looking at is we're looking for the exponent on the x. This has an x term, this one has an x squared term. The exponent on the x in this one is 1, so this is called degree 1. If you have a degree 1 equation, you have a linear equation. Our second equation is degree 2. Because the largest exponent on x is 2, so this is not linear. When you have a real-world graph of a linear relationship, the vertical intercept is always going to represent the initial value of whatever the dependent variable is, usually the starting amount. The slope will represent the rate of change. So let's flip it over and look at an example. A cup of coffee is reheated in a microwave. The temperature C in degrees Celsius of the coffee after t seconds can be modeled by the following linear equations. Explain what the numbers in the equation represent and how do the equations compare to each other. So we have the temperature of two different cups of coffee placed in two different microwaves. One's a 500 watt microwave, another's a 1000 watt microwave. So what do we know? Well, there's two numbers here. The first number is in front of the t. We have 0.5 and we have 1. And the second number is at the end after the t. 20, 20. The y-intercept, or the 20 in this case, is the initial value. So if this is a cups of coffee, both cups start at an initial temperature of 20 degrees Celsius. The 500 watt microwave does something to the temperature, and the 1000 watt microwave does something different. Well, the number in front of the variable is the rate of change. So this is the rate at which the temperature changes over time. So the 500 watt microwave has a 0.5 in front. So 500 watt microwave heats the cup at a rate of 0.5 degrees Celsius per, and our time is in seconds, so per second. And the 1000 watt would heat the cup, or I suppose the coffee in the cup, at a rate of 1 degree Celsius per second. So even though they both start at the same temperature, the 1000 watt microwave is going to heat it up twice as fast. All right, so that's it for linear models. The second part is going to be about linear regression, and that's where you take a line and you fit it to data, and we've done this in previous units, specifically in your assignment when you drew your line of best fit. So that's what linear regression is. It's drawing a line of best fit. And we can use linear regression to model data that appears to be linearly related. So it appears to be close to a line. And the way we do that is we use a graphing calculator. So we're going to use a graphing calculator in this lesson. The graphing calculator we're going to use is Desmos.com. And that's our graphing calculator. So if you're able to, I want you to navigate to Desmos.com. I'll try to do a split screen here so we can see both Desmos and this screen. Give me a second. Okay, I've navigated to Desmos.com and I've hit Start Graphing. What we're going to do is we're going to take this table right here and we're going to insert it into Desmos. And then we're going to run linear regression. So we're going to get a line of best fit on Desmos, and we're going to use that line to answer some questions. Our table is about the median age of Canada's population from 1975 to the year 2000. So we need two variables. We need year and age. And if you have a table arranged like that, the top is always the X, and the bottom is always the Y. So we're going to put years for X and age for Y. If we want to insert a table, what we do is we go to the plus sign and we click table. And if you notice, you're going to have an X1 and a Y1. And for our X's, we're just going to type in our years. So we've got 1975, and we've got 1980. And what's neat is Desmos starts to learn eventually as you start typing in. If you're going up by the same amount over and over again, it might start to anticipate. Mine didn't, because my internet's not very quick. 1995 and 2000. There we go. There's all my years, and now I'm just going to put my ages in the Y column. So we've got 27.4, 29.1, 31, 39, 32.9, 34.8, and 36.8. All right, and now we've got a table, and if we look, we should be able to see dots, but we don't actually see dots. And the reason why is because, well, our X scale is supposed to start at 1975, and our scale only goes up to 10. So if we want to find our dots, what we can do is we can zoom out and just keep zooming out until you see a dot or cluster of dots. And there's our dots right there. So what we can do is we can put that in the middle of our screen and zoom in on those dots. And if you're doing this on a phone or a tablet, you can pinch to zoom and you can find your dots. And there we have it. I'll do zoom one more. There we go. All right. So if we're looking at our graph, it looks like our scale starts around 1990 or 1970, sorry, and it ends around 2010. And 0's at the bottom and 50's at the top. And our dots are kind of over here. 1, 2, 3, 4, 5, 6. That's about what our graph looks like. And now we're going to determine the equation for the line of best fit. And the way we do that is we use Desmos to insert a line of best fit. And we do that by typing this into Desmos. It's basically y equals mx plus b, but it looks like y, and then instead of equals, it uses a squiggly line, and then mx plus b. The reason it's not equals is because we're approximating a line. All these dots might not be on a perfect line, so this is a regression. And since our table uses x1 and y1, when we write our equation, we use x1 and y1 as well. So this is what we're going to type into Desmos. Now, if you have multiple tables, and maybe this was, say, x2 and y2, you'd have to use x2 and y2 when you write your equation. So to enter our equation into Desmos, we click down here to get a new line, and we start y1, and then to find the squiggly line, we have to go to the keyboard, and we have to go to functions. Nope, not functions. ABC. There we are. Squiggly lines right here. And then M. And then X1. And then plus. And the letter B. There we go. We get a line on Desmos right there. And if we look down here in the table, it tells you what M and B are in your equation. So back to our handout, since M was calculated as 0.377143 and B was negative 717.571, we can write an equation using those two values because M is our slope and B is our y-intercept. So our equation would be y equals 0.377143x minus 717.571. And there's our equation for age and years. Now a couple things to note. If you look right here, this is the r squared value. That tells you how close those dots are to the line. And 1 would be perfect. 1 means they're all perfectly on the line, which means some of these dots are a little far off the line. And if you zoom in to these two dots here, that dot's a little bit above, and that dot's a little bit below. So that's why it's not a perfect 1. So those dots are not actually perfectly on a line. This is just a line of best fit. All right, you just use Desmos to make your first line of best fit. Now for C, we're going to use our line. We're going to predict the median age of Canada's population in 2020. So use the regression equation. What we do is we use our equation. Y equals 0.377143x minus 717.571. And since we want 2020, we just put the year 2020 in for x. And we calculate. So I need a calculator here. We got 0.37743 bracket 2020 close bracket minus 717.571, and we get 44.25. So we'll just round to 44. We'll keep it as 44.3. 44.3. There we go. And if we use Desmos, we can also find this answer. How do we do that? Well, on Desmos, we type x equals 2020. And we find the point of intersection. So here we go. In Desmos, new line, x equals 2020. Enter. And we don't see anything, so we zoom out a little bit. There's our line for 2020. It's like doing extrapolation. And we click. And there we go. We get 2020 is 44.257. And we can, this is a rounded exact solution. And this method would be approximate. So there we go. If you want to run linear regression on Desmos, we need to know this equation. And then Desmos will tell you your M and your B. You can write the equation. And if you want to find for a specific year, you can either use the equation that you made, or you can use Desmos to figure it out. Okay, that's it for lesson 6. I've lost track. 6. Let's say 3. Is it 6.3? Well, now I'm curious. Hold on. Yeah, 6.3 linear models. All right, I'll see you next time.